right, let's get started. Okay, so welcome everybody to the last class for Physics 7th Ph.D. So remember, we've covered all the material, and on Tuesday I gave an overview of everything we've learned since the midterm. And I asked you to send me problems or general physics questions, and I would solve the problems in class as long as I got them before last night. So I got a few problems. I also got a request at like 5 o'clock this morning. Sorry. I didn't have a chance to do that one this morning. But I have a bunch of problems here to solve, some of which were quite tricky, some of which are pretty easy. I also have the practice final. Has anybody looked at the practice final yet? Yeah? So I can solve the problems in the practice final. I can solve the requested problems. Strong feelings? Requested problems? All right. Final was too easy? I haven't put up the solutions yet, but I will. Practice final look easy or hard or what?
Easy. Not bad.
All right, good. Well, I hope that bodes well. All right. So, first problem I was asked to solve is 5.118. Okay? And this one should strike close to home. It says, a physics major is working to pay his or her college tuition by performing in a traveling carnival. He rides a motorcycle inside a hollow, transparent plastic sphere. Okay? With in a vertical circle of radius 13 meters. That's quite a big sphere, right? Radius 13 meters. Wow, so that's 26 meters. This thing is like 70 feet high? That seems reasonable? Yeah, have you seen a 70-foot wide plastic sphere with a physics major riding a motorcycle inside? Somebody Google video search that, see if you can find it. Okay, the physics major has mass 70 kilos, and the motorcycle has mass of 40 kilos. What minimum speed must he have at the top of the circle if the tires of the motorcycle are not to lose contact with the sphere? So, he's up here at the top of the circle. Or let's say he's riding a chopper. Right? Okay, so what are the forces on this guy at the top? Right? Here's our free body diagram. Gravity and normal force, right? Gravity is this way, and the normal force is also down, right? Okay, so now we're asked, what minimum speed must he have at the top of the circle if the tires are not to lose contact with the sphere? What's the approach? Right, so let's translate this requirement that the motorcycle is not going to lose contact with the sphere to think that it moves in uniform circular motion, right? Because if it's going to make it up here and come back down, this is a lot like the vertical loop that we had with the fighter pilot, right? And in order to move in a circle, it has to have uniform circular motion. So the force needs to be mv squared over r, right? And what we're looking for in the end is the velocity, right? Is the velocity. So okay, so what does that tell us then, right? This is mv squared over r equals n plus mg. How does that help us? That's right, we're looking for the minimum velocity, right? The normal force could be any amount depending on how fast he's going. So let's set this one to 0 and say mv squared over r is just equal to mg, right? So then the v's cancel, v squared equals gr, v equals square root of gr, which is 11.3 meters per second. Okay, who can translate 11.3 meters per second into something we actually understand? How fast is that in miles per hour?
Pretty fast.
What was the conversion unit you used there? 11.3 per pretty fast?
Yeah, approximately.
Yeah, I like that, approximately. Order of magnitude, pretty fast. Okay. 11.3 meters per second, let's see.
It's pretty close to Usain Bolt's 100 meters.
Yeah, Usain Bolt is 10 meters per second, right?
10 meters.
So that's pretty fast, but not that fast for a motorcycle, right? Well, that's good. We should keep our physics meters safe. And the mass is canceled, right? Oh wait, and then there's another part to this problem. At the bottom of the circle, his speed is twice the value calculated in part A. What is the magnitude of the normal force exerted on the motorcycle by the sphere at this point? Okay, so at the bottom of the motorcycle, at the bottom of the loop, right, we have mg down, the normal force up, right? And we have the same condition, uniform circular motion, and we'll call this VB. And we'll just do mv, let's do this 2v squared over r, right? Same mass, same radius, twice the velocity is equal to n plus mg, right? Nope, it's equal to force needs to be inward, so n minus mg, right? Well, this one here, so this is 4 times mv squared over r, right? And mv squared over r is equal to mg. So this is 4mg is equal to n minus mg, so n is equal to 5mg. All right, so I expressed the force in terms of the velocity required, and I was told already that he needed twice the velocity of what he had before, which means 4 times the force, because the force goes like mv squared, right? I already knew what the force was last time, which is mg, so I just said, this is the force from last time, just replace that with mg, now 4mg on this side. Now last time, the normal force, on the top of the loop, the normal force and gravity help each other to provide the centripetal force. Here, they oppose each other. You need to do more, you need to have a stronger force at the bottom than you do at the top. Right? Anyway, it's not quite uniform circular motion, notice it, because he has different velocity. It's, so we're considering this. So you might object to that and say, how can we have uniform circular motion? Well, you're right, we don't. We have momentary uniform circular motion, right? He's moving in a certain circle at one point and another circle at the top. He has different velocities. Okay. All right, that was one problem requested. I'm doing these in the order of the problems. Next one is 573. This is a real headache. Okay. Here you have 2 blocks sitting on top of each other. Block A, block B, and a force this way. Block A weighs 2.4 newtons. So 2.4 newtons. Block B weighs 3.6 newtons. The coefficient of kinetic friction between all surfaces is 0.3. Find the magnitude of the horizontal force necessary to drag block B to the left at constant speed if A rests on B and moves with it. Okay, so the question is, what is the force necessary on block B so that it moves at constant speed?
Is that the kinetic friction?
This is a coefficient of kinetic friction, yes. So what is the key phrase here? Like constant speed means?
So the balance of the force is equal to 0.
Right, constant speed means no acceleration. No acceleration means net force is 0, right? So what forces do we have on B?
Normal force.
Well, let's draw a free body diagram for B, right? We got our, somebody said normal force, so that's up from the ground, right? So we have a weight down. What else?
Normal force off of A.
We have the dragging force. Fine, the
Normal force from A.
normal force from A on
I
what?
guess the weight of A.
There's the weight of A, that's true. right? So this is the weight B, and there's also weight of A, all right? This is the dragging force, and what else? Friction, right? Okay, so we're interested in the motion of B, but A is sitting on top of B. So the easiest way to handle this is just think of B and A together, right? You could just think of them together, or you could just focus on B and account for A's weight as a force on B, which is really the same thing as thinking of A and B together, and this being a single weight. See what I mean? Either path, as long as you're thinking about it consistently, can get you to the right answer. Okay, so basically, we need to set, we want this guy to balance this guy, right? So if we can figure out the force of friction, we can figure out what his force is, because they have to have the same magnitude to give us constant velocity. So the whole game is, what is the force of friction? Force of friction, of course, frictional force is the normal force times the coefficient, which we're given. What's the normal force? Right, well the normal force here is going to be weight A plus weight B. Right, the normal force is just going to balance the weight of the two blocks. Okay? So that gives, so this plus this is 6 newtons times 0.3. So this is 1.8 newtons. Okay? That's part A. Part B says, let's make this a little nastier. And what is this? Part B says, if A is held at rest, okay, so it's a very similar setup, except now, I'll redraw the diagram so we don't get confused. Now, B is here, like before, A is here like before, except there's a string attaching A to the wall. Oh man, all right? So A is held at rest. Now the same question. Find the magnitude of the horizontal force F necessary to drag block B to the left at constant speed. Okay? It's the kind of problem only a physics person would do, because this never happens in real life. Okay, so now we're going to think about the free body diagrams for A and for B, right? So first let's think about the diagram for B. Okay, remember we have this force again. All right? So let's start off with the forces we had before. All right, we have the dragging force, we have frictional force, right, F, we have the normal force, we have the weight, B, right? What else do we have? What's new? Friction between these two blocks, right? Now, which direction is that friction going to go? To the left or to the right? On acting on block B is going to move to the left. Friction always opposes motion. So this one is going to be, call this one FB, okay, to the right. And there's this force down from the weight of A, right? Okay, now let's think about what happens to block A. Block A has what forces on it? Got its weight, right? There's a normal force up from block B, right? This is, call this NA. All right. Friction. Which direction is friction going? Why to the left? Because it's reversed. Okay, okay, sure. So A is moving to the right relative to B, right? Now the rope is pulling it to the right, so friction is opposing that. So this one we call FA, and then of course this tension, right? Okay. So what do we do here? Well, let's see. We know something about this one, right? This one is just going to be equal to WA, right? Those two are going to balance because that guy's not going anywhere. right?
Won't friction A and friction B be the same magnitude?
Why would they be the same magnitude?
I mean, it's the same, the rubbing of the same particles, I guess.
Okay, and so what principle you're applying there? Principle of universal rubbing of particles? Let's not go down that road. But you're on an interesting track. Why would those two forces, are they the same, and if so, why?
Well, I would say they are because the normal force on B is equivalent to the weight of A, and then the normal force on A.
So the normal force on B,
Yeah, I'm sorry, no. Not the normal force between the ground and the normal force is basically composed of
the normal force here, the normal force which gives us this
Exactly,
frictional force,
yeah, not the one that gives you the friction between the ground and B.
Right.
Is the same as the weight of A, and the normal force on A is the same as the weight of A. And
Right.
it said that the kinetic, the
That's right.
coefficient of kinetic friction between all substances.
That's right, same normal force, same normal force and same coefficient of friction, means these are the same, right? So we'll just write that like that. Okay. So we have, okay, so let's see what we can figure out. We know what NA is, right? NA is just the weight of A, which is given, 2.4 newtons, right? That's why I wrote it NA, right? NB, what's NB going to be? Sorry? Weight A plus weight B, right? Is NB in my notes? Right, okay, so this is NB here, right? Yeah, okay. And B is weight A plus weight B, okay? So now the frictional force, these frictional forces, Fa is equal to Fb is mu times weight of A, right? And so that's 0.72 newtons, okay? So let's keep track of what we know, all right? We know this one, of course. That gives us this one. And we are able to use that to figure out this one, which is the same as this one, right? A is going to be held constant force. So this is also, A is not going anywhere. So that means that we know this one as well, right? Because it's going to be the same. Fb equals T, right? And what were we looking for again? Oh yeah, this one, right? And we know F hasn't changed since last time. F is mu times WA plus WB, right? Which is the same as it was before, 1.8 newtons, right? And so now this guy has to balance both of these two, right? And so it's just going to be the sum of these two guys, right? So F minus Fb is equal to 0, which means F is equal to F plus Fb, which is 2.52 newtons. Okay? So this problem looks nasty, but in the end it's just put down the free body diagram, be very careful about accounting for all the forces. All right, so it's really just about careful work. There's no tricky concept here. All right, next one is 675. A small block with a mass of 0.09 kilograms. 0.09 kilograms is attached to a cord. Here's the block sitting on a table. There's a hole in the middle. Attached to a rope which goes through the hole. The whole thing moves in a circle, like this. Okay. Small block with a mass of 0.09 kilograms. Is attached to a cord passing through a hole in a frictionless horizontal surface. The block is originally revolving at a distance of 0.4 meters from the hole with a speed of 0.7 meters per second. The cord is then pulled from below, shortening the radius of the circle at which the block revolves to 0.1 meters. All right. So R2 equals 0.1 meters. At this new distance, the speed of the block is observed to be V2 equals 2.8 meters per second. Question: what is the tension in the cord in the original situation when the block has V equals 0.7 meters? What's the tension in the cord in the final situation when the block has V 2.8 meters per second? How much work was done by the person who pulled the cord? Okay, so what's going on with this block? What forces are at play on the block? If we draw the block, we've got what? Gravity, normal force, and tension, right? So this thing has a net force on it, right? But it's moving in a circle. Okay, so we have uniform circular motion, right? Which means this force has to be equal to what? mv squared over r, right? And the question we're being asked is, what is the tension in the cord? Well, to know the tension, we need to know the mass, check. We need to know the velocity, check. We need to know the radius, check. So part A is just plug in, right? So just plug in mv squared over r. We have all the numbers. You get 7.1 newtons for the initial case, and 0.1. This is the second case. Just plug in, and you get 0.11 newtons here, and 7.1 newtons here. 7.1. Okay. So that's the tension in the rope in both configurations. Okay. The next part of the question says, how much work was done by the person who pulled on the cord? How do we calculate work? Work done. Force times distance, right? So how do we do that? All right, let's see. Can I just do force times distance is a constant force? No, so I need to do an integral, right? Right? So what is now I need to express the force as a function of distance, right? Okay, this could work. Is there an easier way?
Conservation of energy.
Conservation of energy, how do I do that?
1/2 I omega squared.
Well, is there any potential energy?
No potential energy, but there's a energy you add in by pulling it. So the initial kinetic energy plus the energy you add in should be the final kinetic energy.
All right. I think this is called the work energy theorem or something, but in the end you can derive it from conservation of energy, right? You can say U1 plus K1 plus work other equals U2 plus K2, and if this drops out, then the work is just K2 minus K1. So another theorem you don't have to memorize, but it's given a fancy name for some reason. So we could just calculate the difference in the kinetic energy if we know the kinetic energy. How do we calculate the kinetic energy? It's just V squared, right? Which we have. So this is the easiest way to calculate it. Right? What about this one? How do we do this one again? Well, we need to know the force as a function of the radius, right?
That's just energy squared.
Yeah, but isn't the radius of the velocity also going to change with the radius? We know it is, right? It's not the same for different radii. So that's going to be a bit of a tricky interval to set up. So much better to just use this approach. Okay? Nothing wrong with the other approach. It will work. But we'll get a headache. Okay. Next problem is 786. Says a particle moves along the x-axis while acted on by a single conservative force parallel to the x-axis. The force corresponds to the potential energy function graphed in this figure. So it comes down, negative, up, a little less negative, and up again. This is point A. This is point B. This is C. Okay. This is 1.0, 2.0 here. Okay. A particle moves along the x-axis, acting on this force. Here's the potential energy function. Okay, that's what we're looking at. Question A, part A, what is the direction of the force on the particle when it's at point A? So what's the relationship between potential and force? It's the negative derivative, right? So what you could do is take the derivative of this and invert it. Or you could just ask yourself, if I put a little ball right here, which way would it roll? Down. It would roll down, thank you, yes. The useless but always correct answer. It would roll this way, right? So the force is going to be towards positive x. Let's check that. Well, what's the derivative here? Derivative is negative, right? So we take the negative derivative, that's positive, so the force is positive. So force here is greater than 0 in the x direction. What about at point B, it says? Well, at point B, the derivative is positive, so the force is going to be negative. Also, if we put a ball here, it would roll towards the negative value, so it's negative force. C, at what value of x is the kinetic energy of the particle a maximum? How do we figure out where the kinetic energy is a maximum? Well, if we say kinetic energy plus potential energy is some constant, right? Then the kinetic energy is a maximum when potential energy is a minimum, right? Which is going to be here. All right, given a fixed amount of energy, you get the most kinetic energy when you minimize the potential energy. What is the largest value of x reached by the particle during its motion if it's released from A? That one seems tricky. How do we figure that out? To know how it's going to move, right?
What was the question?
Question is, what is the largest value of x reached by the particle during its motion? Starts out here. 2 point something, yeah. Well, what you do is you say, you can never be any place on the graph that requires it to have more potential energy than the total energy of the particle. Does that require negative kinetic energy? That means you can imagine it's like a Tupperware lid here, it can never break through. So if it starts here, it's going to go down here, be very fast, come back up here, be slow, but still have non-zero kinetic energy, meaning that it's moving. It's going to get over this hump, come down here. When it comes up here, it's going to run out of kinetic energy, i.e. stop, right? So kinetic energy equals 0 means velocity equals 0. That's when it's turning around. So this is the maximum point it can reach, 2 point something. What value or values of x correspond to points of stable equilibrium? Stable equilibrium means no net force, right? No net force means derivative of this thing is 0. So that's here, here, and here. But it's asking for a stable equilibrium. which means the second derivative is going to be positive, right? So this is stable equilibrium because if you move away from it, you're forced back towards it. If you move this way, you go that way. Move this way, you go that way. This is an unstable equilibrium because as soon as you move away from it, you're pushed further away from it. Right? So this one's stable, stable, unstable. Questions about that? Okay. All right, next one, 7.49. A 15 kilogram stone slides down a snow-covered hill. Here's what it looks like. Got some weird shaped hill. Got stone. This is point B, this is point A. Okay, a 15 kilogram stone, 15 kilograms. This is 20 meters high. This distance is 15 meters. Slides down a snow-covered hill, leaving point A with a velocity of 10 meters per second. There is no friction on the hill between points A and B, but there is friction on the level ground at the bottom of the hill, between B and the wall. After entering the horizontal region, the stone travels 100 meters, and then, this is 100 meters, and then runs into a very long light spring with force constant 2 newtons per meter. The coefficients of kinetic and static friction between the stone and the ground are, so kinetic friction is 0.2, static friction is 0.8. What is the speed of the stone when it reaches point B, first of all? Okay, so, complicated situation. But first thing we're asked is, the stone starts with 10 meters per second, rolls down crazy hill to point B. What is the velocity? So we've seen this problem a million times in a million configurations, right? This is potential energy turned into kinetic energy. Nothing complicated about that. So we solve it with energy, right? So K1 plus U1 equals K2 plus U2, right? K1 is 1/2 mv0 squared. This is the initial velocity, right? Initial potential energy is mgh, where h is given at 20 meters. Final kinetic energy is mv squared plus 0, because we just say this is the bottom. Anyway, remember, we're interested in the difference in the heights for the potential energy. So here we have everything we need, right? Mass cancels. V squared is equal to V0 squared plus 2gh, right? So V is 22.2 meters per second. Okay, that part was easy. Next it says, how far will the stone compress the spring? So now we have a stone. The fact that it's come down the hill and whatever happened on the hill is irrelevant now, right? We have a stone moving horizontally across a frictional. It sounds too much like fictional. Fictionally. Anyway. I can't believe I've never wondered where that word was before. Okay, a surface with friction until it hits a spring, and the question is, how far will the stone compress the spring? So, how do we approach this one?
Kinetic energy at the bottom of the hill equals, or minus work done by friction equals the potential energy of the spring.
Right?
Is it rolling?
No, it's not rolling.
Oh,
Sliding.
It looks like a circular basket.
Yeah. The one time my perfect sphere confuses me, right? I'll try to be more sloppy with my drawing. Yeah, so kinetic energy, first potential energy was turned into kinetic energy. Now kinetic energy is being turned into energy from friction and energy of the spring. Okay, but it's a little bit tricky because once it hits the spring, it's still losing energy to friction, right? So we can't just say, you can't do it in two steps. You can't say, how much does it lose due to friction, and then just turn the rest of that into spring. We have to solve it simultaneously. All right, so we have to be a little careful about how we express this work due to friction. Right, so if we define x here as the placement of the spring relative to its equilibrium point, right, then we need to write this as 100 plus x, right, times the force of friction. All right, and we know how heavy this thing is, yeah. So the force of friction is just going to be mu k times mg, because the normal force is just going to be mg, right? So we have 1/2 mv, this is supposed to be squared, not 2, mv squared, where we know this velocity, right, is from here, minus 100 plus x times mu k mg is equal to 1/2 k x squared. Okay, so this is our critical equation, right? And you see that x comes in two different places. So we know m, we know v squared. We don't know x, that's what we're interested in. We know this, we know this, we know this, we know this. We know everything but x. We have a quadratic equation in x, right? So that would just come down to the math part. And if you solve it, you get x is equal to 16.4 meters. Whoa, that's pretty far. That's, I guess, why they said this is a very long light spring.
I'm trying to figure out why there's a spring in the middle.
Right, or how did this rock get going at 10 meters per second already? Right? Somebody should be, this is dangerous playing with rocks. Okay, so the only conception, this is an energy problem, right? The only tricky part here was making sure you took into account the fact that there's additional friction after it hits the spring. Okay, next part of the problem, will the stone move again after it has been stopped by the spring? So it's using kinetic friction, right, and then it gets stopped. And now the question is the force of the spring strong enough to move it to overcome the static friction once it has stopped? How do we figure that out? Well, let's think about the free body diagram of this thing, right? It's going to be a force due to the spring here. Force of friction, static, right? So we just need to compare the magnitude of these two guys, right? And figure out which one's larger. So what is the force due to the spring? Well, it's just going to be 1/2 kx squared, right? That's where it comes to a stop. I'm sorry, it's going to be kx, of course. Work is 1/2 kx squared. So the force due to the spring is 32.8 newtons, okay? How much static friction can you have? Well, this is just mu s times mg, right? Rock is 15 kilograms. We know m, we know g, we know mu s. Mu s is a pretty large number, 0.8. So this gives 118 newtons. So you can have up to 118 newtons of static friction, right? Whereas the spring is only providing 32.8 newtons. Remember, static friction is a funny thing. There's a maximum value, but you can have up to 0, right? I mean, if you have a down to 0, if you have something resting on a surface with friction, and there's no force on it sideways, then there's going to be no static friction, right? It only resists the force. As you crank up a horizontal force, the force of friction ramps up, right? Until it gets to some maximum, after which you can no longer keep it stationary, and then it's overcome. So just because, if you just did this calculation naively, you might think, oh, the force of friction is going to move this guy, because the force of friction is stronger than the force of the spring. Obviously, that's not the case. The force of friction is less than or equal to this maximum value. Does that make sense, everybody? Okay. Next one, 8.97. Jack and Jill are standing on a crate. Jack and Jill are standing on a crate at rest on a frictionless horizontal surface of a frozen pond. Okay, so here's a crate on the pond. We got Jack and Jill. Okay. Jack has mass 75 kilograms. Jill has mass 45 kilograms. And the crate has mass of 15 kilograms. Okay? They remember that they must fetch a pail of water. So each jumps horizontally from the top of the crate. All right. I'm not sure how that's going to get them their water, but just after each jumps, each one jumps, I guess, that person is moving away from the crate with a speed of 4 meters per second relative to the crate. The crate, everything starts out at rest, but if you're going to jump sideways this way, the crate's going to go that way, right? And they were given the velocity relative to the crate. Okay? So the question is, what is the final speed of the crate if both Jack and Jill jump simultaneously in the same direction? And it says, hint, use an inertial coordinate system, okay, attached to the ground. All right, so a coordinate system attached to the ground, we're given the velocity relative to the crate. All right, so in the coordinate system of the ground, say the crate is going this way, and we're asked for the final speed of the crate, so we'll call that v. Jack and Jill are flying through the air. How many times do I have to draw these stick figures? Okay, Jack and Jill are flying through the air. So what is their velocity? If this is v, then what is their velocity on the system of relative to the ground? The crate is v with respect to the ground, so Jack and Jill are going to be v plus 4. Let's make them going positive. It can be confusing otherwise. So they jump positive. Okay. Stick figures. Okay. So this velocity is negative v, right? And their velocity is 4 with respect to the crate. So it's going to make their velocity what? Sorry?
They jump at 4 meters.
Their velocity relative to the crate is 4 meters per second. So their velocity is then what? 4 minus v, right? So their velocity is 4 minus v. This velocity is minus v. Okay, so the question is, and we're given all the masses, and the question is, what is the final speed of the crate? What kind of problem does this sound like? Momentum, right? It's definitely a momentum problem. And we can say that there's no external forces. This whole thing is posed to be on top of a frictionless icy pond, which sounds like momentum already. And so we can say that initial momentum is equal to, right? Initial momentum is equal to final momentum, right? What is the initial momentum? 0, because nothing's moving. So we just need to write the final momentum in terms of the thing we want to figure out. Now we figured out, we know what the velocity, the mass of the crate is. Mass of the crate times its velocity, right? Plus, we can treat these guys as Jack and Jill times their velocity, right? We treat them as a single object in the air if they have the same velocity. And then we have an equation that just has v in it, right? And so we can solve this for v because we know all of the masses. Okay, good. And so if you solve for that, you get v equals 3.56 meters per second. Okay, but this problem is not done. What is the final speed of the crate if Jack jumps first? Then, a few seconds later, Jill jumps in the same direction.
Twice.
You have to do it in 2 steps, right? First, Jack jumps off, you figure out what the speed of everybody is using conservation momentum. Then Jill jumps off, you figure out what the speed of everything is giving conservation momentum. And the question is, what is the final speed of the crate? Again, if Jack jumps first. Okay? So, now we have an intermediate quantity, so we call this v prime after Jack jumps, right? And I guess it's assumed that no matter what's going on, you move 4 meters per second relative to the crate when jumping. Okay, so now the crate is 15, right? Okay, so when Jack jumps off, we can think of Jill as just part of the crate, or the crate is part of Jill, right? And so P initial equals P final, 0, mass of the crate plus the mass of Jill, right? Times negative V prime, right? This is the mass of the crate after Jack jumps, plus M Jack times 4, 4 minus V prime. Is that right? Right, so this is 60 kilograms here, and this from Jack is 75 kilograms. Okay, so we can figure out what V prime is. Again, we have an equation with just V prime in it. And we get V prime equals 2.22 meters per second. Okay? Now, we have to solve the problem with Jill jumping off this moving crate, right? So now we have P initial equals P final, right? P initial is not 0 anymore, because after Jack jumped, the crate is moving with Jill on it, right? So we have 60 kilograms times V prime, right? This is the initial configuration, right? And the final configuration is mass of the crate times minus V, which is what we're looking for, right? We don't know this one, plus the mass of Jack, right? Jack is going at 4 minus V prime, and that hasn't changed, right? Plus the mass of Jill, who's going at 4 minus V. No, we don't need to include Jack in this configuration, do we? We've already accounted for him. This is the momentum of Jill plus the crate. If we added Jack in, it would all be 0 again. This is Jill plus the crate after Jack jumps, so that we just need to account for Jill and the crate. We're doing a system now of just Jill and the crate.
Why is it 4 minus V?
Because we're trying to figure out what the velocity of the crate is, and we just call that minus V. And we know that every time somebody jumps, they get 4 meters per second relative to the velocity of the crate. Okay? So we just did this in 2 steps. This encapsulates Jack jumping off. Now Jill jumps off. We have another equation where we only have V as an unknown. Remember, we already know V prime, right? And so this gives us V is equal to 5.22 meters per second. Okay? So here we got 4 meters per second if they jump individually, and 5 meters per second if they jump one at a time. Why is that?
Because each jump, they have to make sure the velocity relative to the crate is 4 meters per second.
That's right. It's a bit of an artificial situation. it's not like it's the same, each person does the same jump regardless of what's happening, so you can compare whether the crate is speeded up the same amount. It's, the constant condition is that you have 4 meters per second velocity relative to the crate, right, which is different depending on who else is standing on the crate, etc. Okay, and then the next part of the problem says, what if Jill jumps first? But it's just really an exercise in the same sort of game. Okay, that was 897. And we did 749 already, okay. Next one is 10. Oh, we did this one already. 1095. Okay. 1095. Okay. 1095 says a 500-gram bird is flying horizontally at 2.25 meters per second, not paying much attention, when suddenly it flies into a stationary vertical bar. Kaboink. All right, here's our bird. Okay. Velocity is 2.25 meters per second. Mass is 0.5 kilograms. It hits the bar. It flies into a stationary vertical bar, hitting it 25 centimeters below the top. Okay, so this is 0.25 meters. The whole bar is 0.75 meters and has a mass of 1.5 kilograms. And it's hinged at the base. That's sort of unlikely, aren't you? This bar standing at perfect equilibrium through that, waiting for a bird. Okay. Nobody ever said these physics problems were realistic. The collision stuns the bird so that it just drops to the ground afterwards, but soon recovers to fly happily away. I swear I didn't make that part up. What is the angular velocity of the bar just after it's hit by the bird and just as it reaches the ground? Okay, so the bird knocks into the bar, gets it moving, and the question is, what is your angular velocity of the bar? All right, so we're looking for omega bar. How do we figure out how fast this thing spins? What is it that the bird gives the bar? Angular momentum, right? This thing is going to rotate. But does the bird have angular momentum? No. It has what? It has linear momentum. Does that mean it doesn't have angular momentum? Everything with linear momentum has angular momentum relative to some axis, right? Just like the moon is going in a straight line, but it has angular momentum relative to the center of the Earth, right? Okay, so how do we do conservation of angular momentum? Well, we say L initial equals L final, and then we figure out how to write angular momentum in terms of things we want to know. So for the bird, how do we write the angular momentum? Well, it's just mvr, right? Keep the bird as a particle. We know its mass. We know its velocity. We know the radius from the pivot point. This is 0.5 meters, right? So we know how much angular momentum it carries relative to that pivot point, right? How do we express the final angular momentum of this bar? I omega, right? Why I omega? Sure, we want an expression that uses omega, right? Because that's what we're looking for. Also, this thing is not a particle, so you can't just write it as mvr, right? You need to, since you integrate over it, and it's going to have constant angular velocity, but the radii are different. So that's what this does for you, right? This encapsulates something about the shape of the bar. I never remember what that is, but it says here that it's 1/3 ml squared times omega, right? And so we know the mass of the bird, we know its initial velocity, we know this distance, we know the length of the bar, the mass of the bar, so we can calculate what omega is, right? Omega equals 2 radians per second. Okay, but then it says, what is the angular velocity of the bar as it reaches the ground? Okay, why is it not going to be the same as when the bird hits it? Gravity, right? So how do we incorporate gravity into speeding something up? Well, that sounds like an energy problem usually, right? You're turning potential energy into kinetic energy, so you're speeding something up by transforming the potential into kinetic energy. But here we have rotation, right? We have rotational kinetic energy, and we have potential energy. So let's think about how to write that. U1 plus K1 is equal to U2 plus K2. There's no friction, so we don't need to worry about that, right? So first of all, how do we write the kinetic energy of rotation? 1/2 I omega squared. We know omega, we know I, so this term is fine. Right? This guy here we can write as 1/2 I omega final squared. So that's success because we've introduced into the equation the quantity we want to know. So hopefully this is going to tell us something about what we're trying to figure out. Now we just need to figure out the potential energy. What's the difference in the potential energy between when the bird hits it and when it hits the ground? The potential energy of a complex object, and it's changing its direction also. Center of mass, right? Anytime you have potential energy of a complicated object, just think about the motion of its center of mass. The fact that it spins is irrelevant, right? There's no change in potential energy due to motion relative to the center of mass. Only a change in the center of mass will change its potential energy. Right? Imagine, for example, where's the center of mass of this thing? Well, halfway up by symmetry. Imagine if this thing rotated about this point. Would there be any change to potential energy? No, exactly the same, right? In both cases, it's as if there's a point mass at the center of mass because the center of mass hasn't changed. But when it hits the ground, where is the center of mass? It's at the ground, right? So we'll call this one 0, and this one we'll write as mg, and then this has to be the mass of the bar, right, which we're given, and then we need the height of the center of mass, which is L over 2. So the potential energy stored in its initial configuration is just the height of its center of mass relative to the height of its center of mass in the final configuration. Okay, and I think that's all you need for that one. Omega squared. Then you just solve for omega. Omega f is 6.58 radians per second. So it speeds up a lot. Questions about that?
Wait, so the whole bar bends and hits the ground, right?
It doesn't bend, it's rigid, but it
Oh.
flops around that hinge.
Oh, okay, there's a hinge.
Yeah, there's a hinge there. So it's fixed in place. Yeah. And the center of mass also moves horizontally, right? But that doesn't change the kinetic energy, the potential energy. Okay. Next one. 10.39. Find the magnitude of the angular momentum of the second hand on a clock about an axis through the center of the clock face. All right, so the clock, and the second hand. The clock has a length. The clock hand has a length of 15 centimeters and a mass of 6 grams. Let's try 6 grams. The clock hand, yeah, I'm going to take the second hand to be a slender rod rotating with constant angular velocity about one end. Find the magnitude of angular momentum. So, this is a very similar problem we just solved in terms of angular momentum, right? We expressed it as I omega. Here again, we have a rod rotating around one end, right? So this is going to be the same 1/3 ml squared times omega, right? And we're asked to find the magnitude of angular momentum. We know this mass, we know this length, so we just need to know omega. So what's omega? Sorry?
2 pi over 60.
2 pi over 60, right? Omega is literally radians per second, right? How many radians does a second hand go through in 1 minute? Right, well, it's 2 pi radians in 60 seconds. Right, the second hand. So we have everything we need then. All right, we just plug that in. 1/3 ml squared. So this turns out to be about 0.1 radians per second. And so the answer is 4.71 times 10 to the negative 6 kilograms meters squared per second. So this is really just a units problem. And once you recognize that you should calculate the angular momentum in terms of I omega, it's just a question of converting the information they give you into the information you need. Okay. Next one is 13.79. This one is 3 dots. A 5,000 kilogram spacecraft, 5,000 kilograms, is in circular orbit 2,000 kilometers above the surface of Mars. 2,000 kilometers above Mars. How much work must the spacecraft engines perform to move the spacecraft to a circular orbit that is 4,000 kilometers above the surface? So I'll call this H0. H1 is 4,000 kilometers. Okay? And the question is, how much work is done by the engines? Conservation of energy. Okay, so K1 plus U1 plus work other is K2 plus U2, right? And then let's think about what this, the question is asking, what is it? How much work needs to be done by the engines? Yeah, how much work must the spacecraft engines perform? So the only thing that's going to happen in this thing is it's going to change its position, right? This is the only outside work done. All right, just this guy. It's going to move through a gravitational potential that'll be accounted for here. It'll change its kinetic energy that'll be accounted for here. So basically, we just need to solve for W. Now the question really says solve for W. So as long as we can express the kinetic energy and the potential energy in terms of the information we have, then we can solve for the work other, right? So first of all, what about the potential energy? Well, this is minus big G, which is universal, times the mass of Mars, right? Not the mass of the Earth. Mass of the spacecraft plus R, right? Now R here is going to be the radius of Mars plus our height, right? Radius of Mars plus height is distance from the center of Mars. Right, remember we're given these two heights, that's why I've expressed it that way, because we're given these values relative to the surface of Mars. We could just include that here, we could call this height 4,000 kilometers plus Rm, and it would be fine. All right, so we have an expression for U1. The same expression works for U2, right? So that's no big deal. What about the kinetic energy? How do we calculate the kinetic energy? Well, it's a particle, right? It's not spinning. So kinetic energy is simple. It's 1/2 mv squared, right? But how do we calculate the velocity? We're given the mass. How do we calculate the velocity? We need to know the velocity of a radius of an orbit around Mars at a certain radius.
Gravity equals m squared r.
Right. So the condition of an orbit is circular motion, and that circular motion will be provided by gravity, right? So G, M, over r squared, right? So v squared is equal to g, so these little m's cancel, right? M over r, right? So v is equal to square root of g massive M over r, which is the radius from the center of Mars, right? And so then this, again, we can express in terms of the quantities we know, right? So this is determined now just by the height. So let's write this. So 1/2 mv squared is g m over r m plus h. Okay? So that leaves us with this equation right over here. So the initial kinetic energy is 1/2 m gm over rm plus h0. Right? Initial potential energy is minus g m over r plus h0 plus work from the engines is equal to 1/2 m over rm plus h1 minus g m over r plus h1. Right? So now we have an expression for W in terms of the radii. So the radius of Mars we just look up. The mass of Mars we look up. Everything else in this equation we know. And so we can just solve. Right? So the key to this problem was understanding it's an energy problem and that the kinetic energy will also change. One subtle point was expressing the kinetic energy in terms of the height. Right? To do that, you have to think about it in orbit and uniform circular motion. Okay, those are all the problems that I got as of midnight last night. And I should say that only 2 people sent me any problems. And one of those was a single problem. So almost the entire class today was dial a problem by a single person. That person could have been you if you would send me any requests, but you relied on your major that came through for you. Okay, so anything else? Random physics questions?
Do we go to the lab on Monday?
Do we go to the lab on Monday? There's a lab final on Monday.
The final is 2 to 4.
The final is, I think, 4 to 6.
4 to 6.
But
do we still go to the lab?
there is no class next week. Yeah, do not go to class after the semester is over.
That lights been flickering. Why do lights flicker?
Why do lights flicker? Okay.
Like the other ones have the electricity going through them and they're just giving off the light. What's making it so that one sometimes uses electricity and sometimes it doesn't?
Okay, well, how do these lights work, do you know? How do these lights work, do you know? So how does a light work in general? Well, there's 2 kinds of lights, right? There's incandescent lights. How does that work? That's heat, right? That's resistance. Pass the electricity through a wire with resistance. It glows, gives off light, right? That's a very nice kind of light. But these lights are not incandescent lights. These are fluorescent lights. Right? How does the fluorescent light work? It's filled with gas, right? And then it's ionized by an electric potential. So it's a plasma. It's a little tube of plasma created in the gas. And it's alternating current, right? And so it's on, off all the time, right? So that's why fluorescent lights, even when they don't look like they're flickering, can give you a headache because they actually are flickering just really, really fast, faster than you can tell. And so sometimes they go wonky, right? Because it requires the perfect inductance of the electrical current for it to be switching. Any of these things go wrong, and the frequency of the plasma coming on and off gets off from the AC, and then it doesn't work very well. And that's why when you first flip on fluorescent lights, they sputter a little bit before they get going, and then they get in sync. Okay, other random questions?
What's going to be on the lab final?
What's going to be in the lab final? Appropriate lab questions.
Just like everything pretty much we've been doing in lab.
Yeah, just like, it's going to be multiple choice, because you're bringing a Scantron. It's going to be a bunch of problems you should know how to solve. I wish I could give you more information. Yes?
Can you send us an exact copy of the final with all the answers?
I will, yes, after you finish it.
Okay, okay, good.
Other
But
questions?
calculators allowed?
Calculators are allowed, just like on the midterms. You get a cheat sheet on the final, yes, but I will also provide all the equations I think you'll need to know. But you can bring one piece of paper covered on one side with anything you want. That's not pornographic or otherwise illegal. Okay, or human skin. Okay, thank you everybody.